are there and one for the power supply. So that we have connected and use the stepper motor to interface to the LPC2148, and we have written a program to drive the motor and rotate in the clockwise and anti-clockwise direction. Using the proper driver, we have used the 4 transistors or ULN 2003 or 2008 IC I have used to drive the stepper motor to that. So today we will discuss about how a 7-segment display can be interfaced to a microcontroller. What are the ways are there? What are the techniques are there? So which one you're going to adopt it, and what is the lookup tables? All those things we will learn the next 30 to 40 minutes. Any 7-segment display, if you just look at the 7-segment display in the market, so 7-segment displays will be like this. So you can purchase this displays. The moment whenever you purchase this display, they will ask one question: do you want a common anode display or a common cathode display? So they will ask whether do you require a common anode or you require a common cathode displays. So these are the displays which are available in the market for 5 to 10 rupees.
So the screen is not shared.
Okay, sorry. It's visible?
Yes, sir.
Yeah. So we will be learning today how to interface a 7-segment display digits to the microcontroller LPC2148, the variety of methods and the different ways of writing the programs using the lookup tables and without using the lookup tables. The 7-segment table displays available in the market are of 2 types. They will be called as a common anode display and also called as a common cathode display. Each of the 7-segment display will have internally 8 LEDs will be there. These LEDs will be represent one segment of the 7-segment display. For example, the LED A is responsible for the segment A glowing or not glowing it. So there are totally 7 segments are there. One decimal point is a DP, we call it a decimal point. Now, these LEDs can be connected in 2 possibilities. In a common anode, all the anodes of the LEDs are shorted together and connected to the 5 volts. Generally, they connect to the 5 volts. So whenever you connect to the common anode, it is the cathodes to which you supply the data from the microcontroller. So from the microcontroller, I supply the data to the cathodes. So since already the anodes are connected to the 5 volts, that means that it's already connected to the 5 volts. Now to make any of the segment glow, I have to send what? 0 voltage. So if I send 0 on any one of the LED cathode points, that particular segment glows. So that means that sending or making the cathodes or the 7-segment, the pins 0 makes the LED on in case of a common anode. In a case of a common cathode, it's reverse. All the cathodes are shorted together and they're connected to the ground. The anodes are available as the pins of the chip. So in case of a common cathode, you have to send one to make the segment glow. This is the only difference between a common cathode and a common anode. Now, let's learn how to prepare the byte. That is, 1 byte of information is required to make one segment, one digit to glow. So these digits are capable of displaying the numeric and also alphabets also. That is why we call it as alphanumeric displays also. But there's a limited capability of displaying the alphabets. So compared to the LED, now we are migrating to the 7-segment digit. So 7-segment digit is far better than the normal LED because you can represent the numbers and also alphabets also. By properly choosing the segments to glow, you can make the whole digit look like a number or a small, now the limited number of alphabets. You can able to do it. Now let's learn how to prepare a byte pattern to make a particular number or alphabet to display on the 7-segment digit. Let's assume the common anode unless I say other things. So for all discussion, if I don't specify, I am assuming that I am taking a common anode display for the discussion, for writing the program, other things. Now, so let's prepare. I want to display the 3 on the digit. Now, we know that always the segments will be numbered clockwise only. You can always remember A, B, C, D, E, F, G, and the decimal point. They'll be in the clockwise, they'll be numbered. Now I want to display 3. Since I'm assuming a common anode, I'm preparing a byte. My bytes start from a D0 bit here to the D7 bit here. Since the D0 bit of a byte corresponds to the segment A, I have written the A here. The D7 bit of the byte corresponding to the segment, last segment, that is a decimal point, I have written here. So that means that this byte, I am assuming that this is a D0 bit. So I am assuming this will be the D7 bit in the byte. And since already when I am connecting and when I am interfacing from a microcontroller to the 7 segment, I do it in order generally. So that means that the bit 0 is always controls the first pin of the 7 segment digit. The last bit always controls the last segment of the 7 segment. We follow an order. So now I have written that order A, B, C, D, G, F, G, and decimal point. Now 3 has to display. In case of a common anode, to make any segment glow, I have to make that as what? 0, because the cathode, I'm supplying the data to a cathode. I have to make it 0. Now A should glow. That is why I made as what? 0. Now B should glow. That is why I'm keeping B as 0. Now C should glow. So I'm making it 0. The D should glow. I'm making it 0. Now E is not displayed here. That is why I'm making it 1. I don't want F. That is why I'm making it 1 here. And the G I want to display it. That is why I'm making it 0. And we don't want decimal point always. So I'm making it 1. That means that I prepared now the byte, 1 byte. So whenever I send this byte to the 7 segment digit after doing a proper interfacing, I'll get this data on this one. So now I've understood what is the basic required for this one. Now let's go to the interfacing design now. So first we have to understand the concept. What does it mean by concept? What is the behavior of a peripheral you are interfacing? In always interfacing, 3 concepts are there. Understand the peripheral, then build the designing circuit, then build the program. So now I've understood the peripheral, how 7 segment digit peripheral is available in the market, which one I have to purchase, and what are the pins of the 7 segment digit. Now I'll start doing the second aspect of my product development. What is that? Interfacing. I will build an interfacing now. I have written here 7 segment digit I have taken here. So I've taken the Lpc2148 microcontroller. We know that 45 pins, GPIO pins are available. I just randomly, I've selected 8 pins of the 45 pins, that is P0.0 to P0.7, because whenever I interface 7 segment digit, always understand that 8 pins are required. Of course, you can avoid the decimal point and make it permanently connected to the VCC or ground, you can do it. But generally, we take that into consideration also, hoping that it may be useful in certain cases. So I've taken 8 pins and I've connected 0.0 to 0.72 here. Now I've done my interfacing is done. So before doing that one, as usual, we know that we have to connect a crystal. So, and we have to give the power supply to the microcontroller. My interfacing is ready now. Now I have to write a program to make the 7 segment digit display a given number. So let's say we have a variable called some num variable is there. Whatever that single digit I keep it in the num variable, I should able to display, I should able to put this data here. Now, how do we write a program for that? Now, so whenever we write a program, what are the first requirement? First of all, so make these pins or the output pins, we have to do it. Then I had to prepare the pattern required to make, to display the given digits. For example, if I send 1 here, logically 1, say for example, from the micro, you are writing a program. So let's go to the program now directly. Now, so in all my programs, whatever I'll do now onwards, yes or no? I'm just, this is my basic structure. That is always I'll have a delay program. It'll be ready, available with me. So I've declared the prototype of the delay program. And always I'll connect one LED to the P0.31. P0.31, I'll connect an LED. That means that, so I will take P0.31 and connect one LED here. So that means that, so I'm using that LED to check whether my logics are working or not. For debugging purpose, I'll use it. So that's why in the program, so I've just assumed that P0.31, I am just making as an output pin. That is writing a bit 1. So to the direction register becomes what? Output pin. So LED on. I'm just using now onwards a lot of what is called macros to make my program simple. One macro I have written as defined statement. What is the macro I have written? LED on. So LED on is equal to what? Making the bit, that is P0.31 0, because I've connected a common anode LED. Making 0 means LED glow. So this is nothing but writing this statement is nothing but what? LED is on, which is connected at P0.31. Similarly, I made one LED off. So making that bit is equal to, that pin is equal to 1. So this, anywhere in the program, if I say LED on, this statement will be substituted here, that will be executed. So that means that, so I can use this macros in the program whenever I want to make LED on or off. Why I use LED on, LED off? Because whenever I develop a big program, I require some debugging way in my hardware to test whether logic is worked till that point or not. So I'll be using this LED to make it on and off whenever required. So to know that my program is working, my logics are working, like a debugging port, I'll be using this LED. So generally in the project, it is better to have one LED, and you can use that LED as a ladder to try out different logics in the total flow of your program. So now, till this is common for all my projects. Till this is all common for my all projects. Now I want to now interface an LED. So I've just connected already. Now what all I have to do? In the IO direction, I have to now make these pins output pins. What are the pins? 0.2, 0.7. So now what I'll do is, so I have to make that pins output. So I will just logically OR that. So I will prepare another pattern. So that pattern is what? So 0, 0, 0, 0, 0, 0, F, let's say F. So what does it mean that? That means that in this, this F and one more F is required. F, I'll take it F. Okay. So that means that these FF indicates what? 1, 1, 1. How many ones? 8 ones are there. These 8 ones corresponding to what? These 8 ones corresponding to P0.0 to P0.7. So whenever I write this, when I OR this with whatever other requirements, I write into that one in the direction register, 0.0 to 0.7 becomes what? Output. You can always write like this, or you can always use the shift method also. You can able to do it. The another method is, so I want FFF. So since it is aligned to 0.0 to 0.7, you need not left shift any number of bits. I'll just give 0 just to make it common. So what I've done, so now I have set how many bits? 0.0 to 0.7 as 111. So shift to 0 because you're starting from 0.0. So this is another 1 bit, that is 0.1. So like this, I can always add to my statement here as I start using the different number of pins in my project. So now I've added this only to make sure that 0.0 to 0.7 is what output pins I configured it. Now I made LED on. That is, whenever LED on in the project, that means that my logic is started working. Now, so now I'll declare one variable. Let's say I'll declare one variable. So whenever I declare a variable, always in embedded C, keep in mind that I'm addable.
Yes, sir.
Whenever I declare a variable, always keep in mind that limited amount of memory you have. How much of memory you have? 32 kilobytes is there in Lpc2148 for SRAM. So that means that you have to use very intelligently the declaration of the variables. For example, now I want to declare a variable where I can store a single digit number. So shall I use unsigned character? Shall I use characters? Shall I use integer? Shall I use long integer? Shall I use a float? So all these possibilities will be there in a mind. So normal C programming, we always, whenever we want, we can just start with integer, we start always. But the problem with that is you are taking integer means what? 2 bytes or 4 bytes, depend upon the system, what you are working. So the moment I say integer, so you will be losing what? Many number of bytes instead of 1 byte. So what I'll do is, so I should be very careful because my SRAM is very limited. Whether unsigned character is sufficient to do this purpose. Always try with unsigned character. If it is sufficient, go with unsigned character. If it's not possible, then only go for an integer. If it is not possible, 2 bytes, let's say, then only go for a long integer. Always think like that and move forward. Then what will happen is you conserve a lot of space in the SRAM so that as the project becomes bigger, you can able to handle that enough memory for doing a lot of other works. So now, since unsigned character is sufficient for me, unsigned character, let's say 1 digit, I've given a num I've given that. Now, what is my job? So I am developing a small program to demonstrate my 7-segment digit will work or not. Num equals, let's say 1. So that means that now I'm going to write a code below this one to display 1 on the 7-segment display. That means that I have to write my logic now. So I have to display 1 here. So we know that displaying a 1 here is nothing but what? You are making this segment on and this segment on. That means your root. So if I just write a program here, if I write a program here, so I know that it's connected to port 0. So if I write a statement IO 0, so IO 0 set or clear, whatever it may be, set or clear equals 1. So that does not serve the purpose, because why? The 1, whatever there in memory, how does a 1 looks in a memory? In the memory, if you go and verify, how does the 1 will be there in the memory? 0, 0, 0, 0, 1 will be there. Now, sending 0, 0, 1 to this digit will not display 1 there. What you have to do? To display 1, I should have prepare a pattern. What is the pattern? I have to make the B0, C0, and the remaining bits of that what? All to be, I have to make it what? Off. That means that I have to prepare a pattern. That is a byte I have to prepare, 7 segment. The code I have to prepare. That code I have to send it to the 7 segment digit whenever I want to display 1. So just writing 1 in the program and putting into the set register, clear register will not display 1. So I should do what is called conversion. So I should do what is called conversion. So what is the conversion I have to do? Conversion from decimal digit or number to 7 segment code. This is the job I have to do, 7 segment code. So now, how do you do that one? See, there is the 7 segment code for 0 is different. 7 segment code for 1 is different. 7 segment code for what? For 3 is different. So that means that each time you have a number to display, and now you have a number to display in 7 segment code, you have to convert the number decimal digit into what? Into 7 segment code, and then you have to do it. So how do you achieve that conversion? Generally, people use what is called as the 7 segment, what is called as lookup tables. So lookup tables are very commonly used concept in embedded systems to convert from one format of the data into another format, or one numbering system to another numbering system. How do we do that one? A lookup table. Let's build a lookup table now. So now, since every 7 segment code is nothing but 1 byte, that is unsigned character I can use for building the lookup table. So unsigned. So even if I don't say it's a character, okay, I'll say that unsigned character. Now 7 segment codes is a name I can give it, 7 segment code. Now how many 7 segment codes are required for a single digit? Now single digit can display from 0 to 9. So 10 is required. I would write that. Now I have to prepare the codes for how many codes I have to prepare? 10 codes I have to prepare. How do I prepare a codes? For example, if you go here, let's say I have to prepare the codes for the code for 0. Now to display 0, what are the segments to be on? All the segments to be on except for what? G. So I can just say that 1 1 0 0 0 0. So this is the code, 7 segment code to display 0. Because why? See, look at, I'm starting from where? I'm starting from A to decimal point. I'm just starting, this will be the last, will be the decimal point for me, and then the first is the A. So just look at here. To display 0, only the G should be off and the decimal point should be off. That is why I made what? G off and the decimal point off. All remaining I made 0 0 because 0 means the segment glows. So I have got for what? 0 is ready. Similarly, I'll just prepare for 1. So now to make it 1, what is the 7 segment code? So now this B and C should be on, remaining should be off. So now only B and C. So what I'll do is, so all except B and C, I'll make all other things off. So 1 1, so 1 0 0 1. Look at this. I got a code for this one. B and C, I made it 0 0, all remaining. Now convert this into hexadecimal numbers, digits. 0x. So this is nothing but what? C 0. So what is the next digit? So similarly, I can prepare. So 0x. Now F9. F9 is my code. So like this, I prepare for all the digits up to 0 to 1 to 9. I'll prepare it. So let's take the last one. So you can continue. We can continue this one and we can do it. I'll just do the last one. Let's say 9. So what is the 7 segment code for the 9? So 9 means, so A, B, G, F should glow and the C should glow. So that means that upper half of this one A, B, G, F should glow and then the C should glow. So what are the things should be? E and D should be off. E and D should be off. So E and D should be off. So I may have, so A, so I can just take that. So now A should be on, A should be on, B should be on for the 9, C should be on for the 9, A, B, C, then D is off, then E is off, so then I have F should be on, G should be on, then the decimal pointer. Let's say 98. So now I have got the 7-segment code for 9. So I've just prepared that here. So 0x 9 8. So like this, I prepare the 7-segment code for the single digit. This is one time you're going to do it because you're keeping in a lookup table. I'll then document the C0 F9 98 C0. So then I'll go to program C0. So I'll put it here in the table 0x C0. So 0x F9 like that. I'll write it. So till the end, I'll write all that. I just written now 2. So similarly, you can able to fill all those values and write the whatever the value required for that. For example, so the last one is 9 8. So I'll just leave that last one. So we can write like this. So now like this, all you can write it. And now this table contains what? Codes, 7-segment codes. It is there in this table. Now, it is very important that I'm storing the codes in an order. That means that the index 0 contains the 7-segment code for the 0. This is the link. Why it's called as a lookup table? I'm storing those codes in an order. Indexing into this table using the decimal digit will exactly go to the place in the array where 7-segment code is available. So that means that arrays can be used to convert one number system to another number system, because why? Indexing into a proper place, at the corresponding place you already prepared the codes and keeping it. So this concept is used here. So if I say 7-segment of codes of 0, I'll get what? The 7-segment code for 0. If I say 7-segment code of 1, index into this one, I'll get what? 7-segment code for the 1. Like this, I have stored all the 7-segment 10 codes into this array. I stored it. Now my program starts. Now I have to implement the logic. What is the logic I have to implement? So we know that whatever the value you have taken, that means that, so the corresponding, whichever the bits you have taken, so you have to properly use it and output to here. Now in this case, so since I'm used common anode, writing 0 means, so it's important here, to any one of the bit. If for example this bit is 0 means what? The corresponding bit will be on there. Now, so only for in this case. So what should I do it now? I have to take a register now. So which is the register I'm going to use? I have to use a set register or a clear register. I have to use it. Now I'll make complete all the digits is equal to what? So I have to make the selected bit is equal to what? The 0. So selected bit is equal to 0 means, so I will use what is the register called IO0 clear register. I use it. Now, if I take a common cathode, so in this case, I can directly write it. If I use a common anode, I just have to invert it. So IO clear, I use it. Now, I'll get the number variable, and now convert this number variable into what? 7-segment code. So which is the 7-segment underscore the codes. I've taken it. And then I'm going to the lookup table. I got the number. Now this number, based on the whatever the number decimal number you have it 0 to 9, I'm converting to 7-segment codes. Now I got the code. Now this code I have to output to the IO clear register. Now whatever the code you got it, yes or no? This code, it's already there connected to P0.0. That is why even you left shift 0, you can give it, or even if you don't give it also is okay. Because why? These codes are connected to what? These codes are output directly to what? P0.02, P0.7, because they are connected to the lower byte. I don't require any shifting the data. It's not required. So I can remove the data shifting because already there. I have to just output to the clear register. Only thing is, since we are using in the 7-segment, but 0 means it glows, 1 means it is off. But in the clear register, we have to make it to make any point equal to 0. What should I make it? So any bit, any pin, I have to make it 0 means in the clear register, I have to make it the corresponding bit is equal to what? 1. So I'm just making it here. I'll make it invert. I can do like this. I can do it, or I can able to, when I'm preparing the code itself, I can prepare the way I require it. So now, so what I'll do is I'll just remove this for a moment to make it simple. I'll make it simple. So I will assume it's instead of common anode, it's a common cathode. Otherwise, I have to reverse it. So So what is the way I have to reverse it? Because all other bits, I am making it as what? So only the required bits I have to make it 1, the remaining bits I have to make it 0. So now I'll assume for the time being as a common cathode, so that I'm just the corresponding the bits 1 wherever there. So 0 means 1 means it glows, 0 means it will be other way. So I've just set this register. Now I will take it set register for time being to make it simple discussion. I will set register, I've used it. So I'm just assuming now for a time being this is a common cathode. So that sending 1, so sending 1 makes the so I have to prepare, sorry, I have to prepare the other way, then I have to invert it. So let's have this display as it is. So what I'll do is I'll just take it as it is. So common anode only. So I'll go for a clear register. So zero. Just I'm making it this byte, this one. So now what will happen is this code, whatever I have, I've just inverted it. That is, whichever the bit I'm making it 0, it becomes a 1. The remaining bit it become a 0. I've just prepared this. I'm just writing it to clear register. So now I'll stop my program at this point. So I'll just say while 1. Now we will run this program and see that so whatever the value I sent, I'll be getting it. Okay. So now for demonstrating that, I'll remove this one. So I'll just show this one here in the debug, and then we'll make it. It's easy to see in the debugger. So I'll go to so I have just taken the first instruction. LED is on because the last bit is 0 here, and the num is 1. So now 7 segment codes, whatever the code I have, I've just given the value is a num1. So num1, the corresponding code in the table is what? F9, because this is 0, this is F9. I'm just setting it this value to here and sending it. So what is the code I'm supposed to get now? This is a code I'm supposed to get it. So now I got F9. So 1110 and 100. This is a code, I got it. So this data, whatever I output here, it is coming to these pins and make it the corresponding digit on and off. So by making this one, then what will happen? The segment will display. I think we can directly write there. I think this instruction is perfect because all the bits which are required are 1, the remaining bits is 0. Only thing is, so before doing that one, I can just write 0, 0 into that position. That's the only thing I have to do it. I think so. Common anode and the logic what you followed is correct. Only thing I'll write zeros in the beginning before do it. I think then it will be perfect. So I will just write IO0 clear. Clear. So 0x 0 0 and then 0 0 ff. So now what is that I have done is, so I have just made all the bits, that is 0.0 to 0.7, all the bits I made it 0 because I'm writing into the clear register 0, and then I'm writing into the set register. I think this logic works well, perfectly, it suits here. So I'm making all the bits 0 and then I'm writing it, so that I'll just make the required bits only on the pins, remaining bits is automatically 0. I think this is the perfect one. Now let's say I have to implement now decimal up counter. That is, I have to display 0, 1, 2, 3 and the digit up to 9, and then I should stop. So if I want to do like that, so what are the things I required? So I'll say one for loop for unsigned character or integer, whatever, I equal to 0. So I less than are equal to 9i plus plus. So now, so I want to implement a small program to implement decimal up counter, single digit up counter. So now what I've done, only thing is in the program. So in the program, what I've done, I'm only thing is instead of num, I'll replace with what? IL. So now what will happen when I run this program? So 1 by 1 digit will be taken. Only thing is you have to give proper delay here. So I'll just make the delay as a comment here, delay. So ms. So some delay you can give it, let's say 1 second or something like that. So I just made it a comment. Now we'll see that how a single digit decimal up counter you can implement using this program. Now, so as I go through the program, first it will display 00 here, 7 segment code, and then 1, it continues like that. I have written 2 codes, so I'll show for the 2 codes. So now I'll run this program. So I'll go for the first one. So it picks up, so now it picks up I is equal to what? The 0. So the code for that is what? C0 is a code for that, the first one C0. So you can look at here. So you should get the C0. So I got 1100 C0. That means that 7 segment digit when I will display what? 0. Now if I go for the second one, so it display what? The F9, that is nothing but 1. So the program continues and you can able to implement what is called as, so single digit, the counter you can able to implement it. This method you can always use to interface and implement in the program a single digit display. You can always write a whole of this code in a function and you can call 7 segment function. You can write one function also like that. Now, this is the basics of 7 segment we have understood. Now we'll make the problem a little more complicated now. Now, if I want to add few more digits into the display system, now the challenge is, I'm audible?
Sir.
The challenge is the number of lines. Using this technique, there's a one disadvantage is that. So what is the disadvantage in this technique? 8 lines of a microcontroller is required for one single digit. 8 lines are required for one digit. 8 lines are required. If I want to add one more digit, then how many lines are required? 8 more lines are required for you. 8 more lines. 8 plus 8, 16. Generally, most of the times we use at least 5 digits to implement the different logics in the project. At least 5 digits should be there to display a large number and also to display a simple alphabetic alphanumeric displays, alphabetic displays. For example, 5, help, some other words you want to display, at least 5 digits should be there. Just imagine that 8 pins are required for 1, 2 digits, 16 are required, 5 means how many required? So 5 into 8, 40 pins are required. That means almost the complete microcontroller, all the pins you're consuming only for the 7 segment digit. Now there is an LCD is there is a motors there, there is so many other devices there. You cannot build a 7 segment digit display using this technique. So what is the limitation of this technique? It consumes 8 pins. Even if you use a decoder ICs outside, in between that, again you require 4 pins, BCD to decimal decoder or BCD to 7 segment decoders you can use in between. But then also 4 pins are required. That means that number of pins required to realize a multi-digit 7 segment display is not effective in this case. So what is the way? Now only way is available is we should use some other concept where you can able to use less number of pins and able to realize multiple digits. So one popular technique used in the industry, so using the concept called the shift register. Let's understand that concept now. Now, I don't want to use so many pins for a 1 digit. Now, what is the way I can do it now? One method is now introduce a memory element here. So now what I'll do is now I will take, let's say, I will take this digit. Let's say I will take this digit here. Let's say I want to interface this to the microcontroller using less number of pins. So what I'll do is I will introduce one memory device here. One memory device I'll introduce here. So what is this memory device will do it? This memory device should be of that type. If I type that one, you can able to push the data into this memory, and this memory can hold the data which is required for a shift register here. Here the problem is what? 8 pins are required to display here, and 8 pins you should hold the data here. That means that once you dedicate 0.07, 0.02, 0.7 for one display, I cannot use the same pins for something else, because why? You have to hold the data. If you remove this data on the pins, what will happen? The display will go away. So now what I'll do is, to reduce that one, I use what is called some memory device. What is the size of a memory device? The size of the memory device should be 8-bit. I should require an 8-bit memory device is required. So now I will go for some 8-bit memory device. I'll go for it. Now, how do I put the data into 8-bit memory? I have to push the data into that 8-bit memory device. Always, how can we push the data? Let's say I have taken microcontroller. Now I want to push the data into this one. So from the microcontroller, I will push the data such that I can able to push the data in a serial fashion to this memory device. So if I use serial fashion, the advantage is what? You can push the data 1 bit at a time and ask this memory to collect the data and keep it here. So how many bits I have to push? 8 bits I can push it here. Whenever you want to push the data into memory, always you require two concepts are there. One is the data you have to send to the memory, and also you have to give an instruction to the memory. That is, I am sending what? 1 bit at a time. That means that you also require one more line that we call as a clock line. Now you're getting that idea. Now, so I'm just putting the data, and also I'm doing what? I'm pushing the clock also. So two things I'm pushing here. So one is I'm supplying the data line, I'm supplying the data. Other is what? I'm supplying the clock for that. So what does a D indicates? That is 1 bit at a time I'm pushing here, and then I'm giving what is called as clock signal here. So using these 2 bits, I can able to what? Push data in a serial fashion and collect 8 bits of data in the memory, and then this memory can be used to send the data here. Now can you tell me, what is this memory? How do you realize memory? How this chip is available in the market? This you studied in the digital electronics. This 8-bit memory can be realized using 8 flip-flops. Each of these flip-flops are connected internally in a serial fashion. That flip-flops connected together one after the other in a serial fashion is called as shift register. So we know that a shift register is a very commonly available IC in the market. So this shift register can be used to realize 1 byte memory. Now what I'll do is, after using one shift register and receive the 8-bit of data from the microcontroller and giving the data for 1 digit, now I want to repeat for the other one. So what I'll do is now, what I'll do, I will take the whole set of thing as it is. I'll purchase one more shift register. I'll purchase one more shift register and one more display. So now I place next to this one now. So only thing what I'll do is now, since the data comes only from the one position, one end only. Now what I will do is I will select the data, the last data from the microcontroller, and that is a shift register, and give it to the input of the second shift register. So what I've done, so the data, first data, that is which is coming from the microcontroller, gives to the input of the first shift register. Now, after you give 8 clock pulses, one data is ready here. Now what I'll do, I'll cascade this shift register to another shift register. The output of the first shift register, I've connected to what? D input of the second one. So what is I've connected here? So I've connected here the D input. So the output of the first shift register I connected to what? D input I've connected here. Look at that. Similarly, I'll repeat. I'll place another set. I'll place another set. I'll place another set. Only thing what I'm doing is output of every shift register I'm connecting to what? Input of another shift register. So by doing like this, I am preparing multiple shift registers so that I can able to supply the data to the multiple digits. Now, if let's say I require to design a 5-digit display, then how many shift registers are required? 1, 2, 3, 4, 5. 5 shift registers are required. Now, once my design is ready, now if I look at from microcontroller point of view, how many lines you require to push the data? Only 2 lines are required. One for the data, one for the clock. And the same clock you can give it to what? All the shift registers. Same clock line you can give it to all the shift register. So once first 8 bits data is filled here, next 8 bits you push, what will happen? The 8 bits which is already there in the first register will go to what? The next shift register. Similarly, when you push the data, again another 8 bits, the data what is there in the second shift register will go to what? Third shift register. So this concept is called as cascading of shift register, and designing the 7-segment display using only 2 lines of the microcontroller is very popularly used because we reduce the number of lines to realize a display system. Now we will understand with a full block diagram here now. Now this is the complete block diagram of the circuit. Now what is we have done here? So I've selected 5 shift register. 5 shift register, I've taken that. Each of the shift register is connected to one display here. You can look at that. It is connected to, this is the first digit. So this will be the second digit, and this will be the 5th digit. I've connected that. So all the shift register outputs are connected to the displays now. The data line coming from the microcontroller connect to the first shift register data input. Output of every shift register connected to what? Input of the second shift register. It continues here. The clock of all the shift registers joined together and given as a common clock. It's a clock pulse. We call it a CP or a clock pulse. Now, so there is one more concept called a strobe have been given. So whenever you go for shift register, a lot of shift registers available in the market, which is you're going to use. So I've just searched one which is commonly we have used in many number of projects. So you can always you can see that this is a one shift register very commonly used in the market. It's one from the Texas Instruments. Similar such shift registers are also same number 744094 ICs available from other manufacturers also. So I've just given the data sheet of a Texas Instruments. See that this is a shift register. This shift register has got how many outputs? 8 outputs, Q0, Q1, Q2, Q3. So Q4, Q5, Q6, Q7. You can see that this shift register. And this shift register has one ground point and one VCC point is available. Now, one data point is available for feeding the serial in data. And this is also called as what? Serial in parallel out device. So this shift register is also called as what? Serial in parallel out shift register, because serially you can push the data and parallelly 8-bit data it gives it. Now, output of the shift register is available, the 2 points QS1 and QS2. There's a little difference is there. So we are going to take the QS2 as an output of the shift register to connect to the input of the second shift register. Now, apart from this, there are 2 other signals are there. So which are called as, one is called as strobe. What is the meaning of a strobe? So strobe is an input which is provided to certain industry grade shift registers, where whatever the data you shift, it is not available on the pins called Q0 to Q5 unless you copy into, there is a latch. That means that inside the shift register, there are 3 components are there. One is a shift register, that is a set of flip-flops. Other is a latch, which can memorize the data, whatever you shifted it. Other is what is called tri-state buffer. So generally, most of the industrial grade shift register will have this one. That means that first is 8-bit shift register. So that means that 8 bits of that shift register is connected to what? There's a storage which is called as a latch. So during the shifting, the data is not visible on these pins, because why? You are not copied the data in the shift register into what? Inside the latch. Why we do this mechanism they provide? The shifting will not be seen in the outputs. Once you shifted all the data, then you copy that into a latch, internal latch. How do you copy? There's a pin called strobe is provided. For example, in this case, strobe is active high. That is, whenever you make the pin is equal to 1, that means the data what is present in the shift register, that is 8 flip-flop, will be copied to a latch inside present here. Then it's available here. So that is a concept called strobe pin. So how do you use a strobe pin? First finish the shifting, then make the strobe is equal to high and then low. Then the data will be copied to the pins. So before it copies to the pins, there is what is called 3-state output or tri-state outputs are available, or buffer is implemented in this shift register. This is a very commonly you can see in the ICs or integrated circuits when you design the system, what is called tri-states. Every pin, the digital pin can have a 3 states: logic 1, logic 0, other is called as high state output or called as a 3rd state. So that means that if you are using this pin, either you put what? 1 or 0. When you're not using these pins, so since these pins maybe would have, whenever you use these pins would have connected to other bus, other signals and so many things. When you're not using in the logic, what you have to do, you have to make it what? Disconnect to the circuit. What do you mean by disconnect? You produce your high impedance. High impedance what? It's nothing but like a disconnect. So that is called 3rd state. 3rd state is called as high impedance outputs. So 3rd state is nothing but logical disconnection. It is nothing but wire itself, the pin itself is disconnected. There is no 0 or there is no 1. So these are the 3 states outputs are there. That means that when I'm not ready with the data, always we can make that what? OE. OE means output enable. I have make it ground. Whenever OE is output enable is 0, it's all disconnected. Whenever the data is ready, I can make it what? 1. then what will happen? The data is disconnected. Generally, most of the circuits, what we do is, since we are connecting permanently to the 7-segment displays, I'll make this point is equal to what? High always. Whenever you make output enable point always high, what will happen? This data is always available, always available. So how do I use this circuit? Now this shift register, I'm using these 8 outputs connect to the 7-segment digit, permanently make output enable is equal to what? Logic 1, so that always this logic is enabled and this is always connected here. And first I will shift the data into this shift register using 8 clock pulses and keeping the proper data at for the 8 clock pulses. Then after the shifting is done, I'll make the strobe is equal to high and then low. So then what will happen? The data will be copied and it's available to the pins. So this is how this shift register I'm going to use in this project. So whenever we design the circuits, always remember that understanding the basic of the basic components will enable you to design different circuit. So now in your life, from today onwards, any time the requirement of a shift register is there, you can go for 4094 IC. 74HC4094. You always remember that it's a serial in parallel out. So it contains internal latch, it contains a tri-state output buffers, and so you can feed the data into the shift register using what is called data on the clock. Now my design is ready. That means the complete 5-digit display system, I have designed it. So 3 pins I've taken from where? These are the 3 pins I've taken from the microcontroller. So we have assumed for this purpose, let's say I've assumed some pin port 0, P0.19, we have assumed for this, 20 I assumed for this, P0.30 I've assumed for the data. So we have to make certain assumptions. We have assumed for this one because in the board what we have designed in the lab, we have used these pin numbers. Now once the complete design is over, now I have to build my project. So I will take another 5 to 10 minutes for the project, or if it's already 1:30. Okay, we will continue tomorrow the discussion. Then it's already 1:30. Okay, I'm audible.
Yes, sir.
Yes, sir.
Yeah, so we will continue the program. Program is bigger, is there? Little concepts are there. So we'll continue tomorrow. So summarizing today's discussion, we are able to interface a single digit directly using a port without the shift register. Only 1 or 2 digits are required. You can always go with that method. If more number of digits are there, you can always realize that system using a cascading of shift registers and then design the system. So we'll take the attendance. Those who finish attendance can leave the meeting.